It's Q&A Friday. So just got off the phone and a little discombobulated, but we've got some good questions. I think, and there's a couple, I was just quickly looking at it right before I went live. There was a couple good statements in here that I think we can take a look at today. And let's get started. So today is the 20th of August. And first question, actually, I'm going to go to my email because I received this one, which I thought was an interesting topic. And the basic question was, so this individual sent me some trip curves. And it said, hey, Tom, am I correct that this time current characteristic curve is not selectively coordinated with a question mark? So let's take a look at what we've got. And this is what was sent to me. So let's do this. All right. So these are the curves. And again, the question is, or the statement was, this individual said, is he correct that these do not selectively coordinate? And, at first blush, basically, I see a bunch of overlapping of curves down at the bottom of this TCC curve. But what you have to be careful of is the amount of information that you receive to be able to, hey, Nihad El Sharif, good to see you, buddy. The amount of information that you receive on a curve and what your response is. So I have to be careful with how I respond to this one and this individual, because I can't answer the question. And the reason is because I don't have enough information. What am I missing on this curve? Usually we'll plot a little one-line diagram, which I don't necessarily need because I know that the blue breaker is the 30 amp breaker. That's going to be furthest from the source. And I can ascertain that the 200 amp breaker is the next one upstream. And then I can also ascertain that the 800 amp breaker is up further than that. So they go 30, 200, and 800 amp breaker. And I see, overlapping of curves, which in my opinion, knowing SKM, they probably did not put in the available fault current into SKM. There's probably not a single line diagram. In my opinion, this individual more than likely simply added 3 curves to a TCC in SKM, which is possible to do, and plotted them. And that's why you see the entire curve all the way up to 10,000 amps. So my answer to this is I don't have enough information because why? What am I missing? A key point or a key aspect for selective coordination is I need to know what the available fault current is that I'm comparing for each of these overcurrent protective devices. And here's what I'm going to do is I'm going to quickly what I'm going to do is try to bring up a little one-line diagram and help you understand the perspective here. Actually, I don't even need to do that. So let's say, for example, these 3 breakers are in series with each other. When you're dealing with circuit breakers, an important part for selective coordination is to understand that in this world of selectivity for these breakers, these 2 breakers, whenever we do selective coordination, you always selectively coordinate in pairs. You look at the furthest, and you start furthest from the source. So you look at the very last device in the system, and then the next upstream overcurrent protective device. You plot those, and then you compare those two devices with the amount of fault current that will pass through them. So I'm going to simply do, wish I had my pen. So what I'm going to do is, and in fact, I'll do this over here. It'll be easier. That way you can see what I'm doing. And all right, so what do we know that we have? We have a, let's draw a breaker. Control CV. We're going to draw a circuit breaker. We're going to put in an arc. And this is how we do it. Okay, does that look like the symbol for a circuit breaker? Does to me. And then what we'll do to just give it some weight, substance, and then we'll group it. Group. All right. This is a training class in PowerPoint too. See? So there's my breaker symbol. Control CV. I'm going to make another one. I'm going to put that up here. And then we're going to draw a conductor from the end of this to feed this bus. And you know what we'll do? We'll give it a different color. How about that? And then we'll give it a different weight. And let's draw some text. So this, and if you recall, there was a, I believe it was a GHB 30 amp breaker. Let's just double check. Whoop. So I had a, the blue device right here is a GHB 30, and then the red device upstream of that is an FD 200. So that's a GHB 30. And then I'll have an FD 200. And then this is how we roll. Control CV. And then up here we had a, let's take a look at, that's this green one. That is an NG, Nancy George, 800 amp breaker, 800 amp trip with a 310 plus trip unit. So we'll just do an NG 800. And we'll say a 310 plus trip unit. Why is that important? Why is the trip unit important? Because the trip unit is what's going to establish the curve. Okay, so that's an important piece of this pie. So I could go into the, I may be able to go into the library of SKM and call up an NG breaker that'll have a 310 plus trip unit, or maybe an Optum trip unit, and each of those, or some other trip unit, each of the trip units, that's the brain that establishes the time current characteristic curve on how that specific device is going to respond to current. So here we go. So this is what we have. Now, if I look at this time current characteristic curve, I'm not showing and plotting any fault current on this curve. If, for example, let's say that, I don't know, 1200 amps. Let's say that the fault current at this bus, I short circuit equals 1200 amps. I'm just 1,200 amps. So I'm just taking a stab in the dark, and I made that number up, obviously. Why did I make it up? Because if you look at this trip curve, I can use the time current characteristic curves to determine selective coordination for circuit breakers when my fault current is less than this leading edge of the upstream circuit breaker. Why is that? And I wonder if I can draw. Can I draw? Can I draw? I don't want to add a signature. I want to, let's go to comment, edit. I'm going to go to edit, and I'm going to see if I can actually draw a line. Can I draw a line? I can add an image. I can add text. Can I draw? Oh, looks like, oh boy. Oh, but looks like I might be able to. No, I don't know if I can. Well, let's just say, for example, my fault current, and I'm not sure. So if this is 1,000 amps right here, the next line is 2,000 amps, and you'd have to look at the. Actually, I'm going to make life a little bit easier because I'm going off of an Adobe Acrobat. So what I'm going to do is I'm going to call SKM up directly, and we are going to add. We are just going to go to. We're going to close this. We're going to go to time current characteristic curve, and I'll show you how do we do it. We just basically create Q A Friday. Right? We're going to create a new one. And so what I'm going to do is I'm going to add new static trip. It was an FD 200. Let's take a look at the curve. That's an FD 200. And based upon the looks of this curve, I know it is a thermomagnetic circuit breaker. So there's no electronic brain on that. So I'm going to go to thermomagnetic circuit breaker. And I'm going to go to device. I'll set the bus voltage. What voltage did they use? 208 is their reference voltage. So 208 will be our reference voltage. And we will go to library. Oh, I got to change this too. Look at that. See that? 480, 208. Okay, so now my reference voltage on my TCC curve is 208. I'm going to go to the library. And remember, anytime you're using SKM, it will not work correctly unless you do one very critical piece. You see, when you're selecting things from the library, you need to come up here to where it says manufacturer, and you have to select Eaton Cutler Hammer, or Cutler Hammer. If you pick any of these other manufacturers, it's just not going to work right. I'm just saying. So now we're going to pick the FD breaker. There's an FB, FD, HKD, FD. Let's go to I'm just going to pick a Cutler Hammer. Where's my Cutler Hammer? There it is. Cutler Hammer, FD breaker. There we go. Look, see, there's an FD breaker. 15 to 225. I double click on that. And what was the, I think it was a 200, if I'm not mistaken. I come up here to 200, and I'll do a 240 volt, 200 amp, 65,000 amp. And if you recall, they had current times 10. So I'm going to change, double click down here. I'm going to do current scale, 10 to the first power, and there she blows. Look at that. And that looks, let's do this. Looks very similar, if not identical. For my Cousin Vinny fans. Let's do this. So there's the curve. Let's take a look. Look at their curve. Yes. See that? See how it triangularly comes down? Triangularly is a new term. Hey, just joined from Ireland. Welcome. Welcome. Glad to see you online. We are truly international. We have Nihad El Sharif from Egypt, and we've got Ireland on the call. Excellent. All right, so we're talking about selective coordination here because this was a question that came in. So what I'm trying to determine is, what is this leading edge? Because I know I will selectively coordinate with that GHB, and let's plot it. That's a GHB 30. So here's how we roll. We'll do a new, and we come to a thermomagnetic circuit breaker, bus voltage 208. And I will go to the library and look for a GHB. There it is, 3-pole, there she blows, Cupcake Island. And we will make this a 30 amp, 240 volt, 30 amp breaker. There we go. So there's our two breakers. which basically replicates the curve that was sent to me. All right, so I have both of those devices. And now, so this is, I got to look at the leading edge. And if I look, this leading edge starts at 1,803.7 amps. 1,803.7. So I know that these two devices right here, those two devices, I'm going to put that to the back, and I am going to fill this with, I don't know, we'll do it like that. And we'll take this. We know, based upon TCC, selective coordination is achieved from 0 to 1,832.5 amps. 1,832.5 amps. Why do I say that? Because when the current goes into this region of the curve, based upon the TCC, time current characteristic curve, I cannot tell you if the GHB will stay closed and the FD200 will, if the GHB will open and the FD200 will stay closed. I just don't know based upon the TCC. I cannot honestly tell you the performance because they overlap at this point. So for me to determine whether or not those curves I will achieve selective coordination, I would need to go to other methods. And we use the circuit breaker tables for that resource. So I would have to go to another source to determine whether or not they selectively coordinate, or I could change the upstream overcurrent protective device or the downstream overcurrent protective device. So that's a 30 amp. I could do this. I could say, look, and I know this because we've tested it, I could replace that GHB 30 with 208. I can replace that with a fuse, and I'm going to do a TCF, Thomas Charlie Frank. And I could change that with a TCF 30. That curve right there, that will selectively coordinate up until the interrupting rating of that FD 200 amp circuit breaker. Because the fuse will go so fast, and I know that because we have actually tested that pair to make sure that they would selectively coordinate. So I have a couple choices. I could change the circuit breaker upstream, making it a larger circuit breaker, or I could change the circuit breaker downstream to make it a faster acting device. If my fault current, only if my fault current is greater than 1,832.5 amps at this location. So let's make sure that we know exactly where we're talking. Control V right here. I short circuit equals 1,800 to, so if the fault current at this location is anywhere from 0 to 1832.5 amps, they will selectively coordinate based upon the time current characteristic curves. If my fault current is greater than 1,832.5 amps, then I can't make that determination based upon the curves. Then I'm into using the circuit breaker tables. And I would have to, and I'm not sure if I can find those. I'm going to try to find them. Because I know we replaced some of our literature here. FD, an FD breaker. I need an FD 200. I may not be able to find it right off the bat, but I'm just looking, and I'm looking at our selective coordination tables, and I don't seem to. Oh wait, maybe I do. Selective coordination chart, upstream device, 200 amp FD. Oh, that's the wrong. That's 0.1 seconds. Can't use that. It's 0.1 seconds. That would work for 0.1 seconds. Easy. I don't have to worry about fault current. I don't have to plot fault current. I don't have to do anything. All you have to do for a 0.1 second application, you hide everything below 0.1 seconds. Hide everything below 0.1 seconds so nobody can see it. Don't calculate fault current. Don't plot fault current. Don't do an evaluation with fault current. And just make sure that there is separation above 0.1 seconds. You're golden. I mean, it's very, in my opinion, as compared to trying to make sure these selectively coordinate, it's very simple, very easy to determine coordination because all you're looking for is separation of curves, and you don't have to calculate fault currents. You don't need an engineer to do it. You can just, in fact, everybody publishes information. And I don't have my FD downstream of a GHB. So in any case, because we have new breakers now. So in any case, you can go to the circuit breaker tables and they will tell you at what point they will selectively coordinate to get that done. Now, the next step in this process is to look at, let's do this, Control CV. The next step is to look at these two breakers, okay? And say, what do I know based upon the time current characteristic curve? Based upon the TCC curve, let's call up SKM again. I have to add, what was it? That was an NG800 with a 310 plus trip unit. So I say new, and I come up to a static trip, low voltage circuit breaker. I put my bus voltage in, 208. I go to the library. And remember, the only way to get this to work correctly is to select either Eaton, Cutler Hammer, or Eaton/Cutler Hammer. And then you come down to the NG. NG. There we go. There's the ND. There's an NG 800. NG 800, 800. That's a 1600. Hold on. Look at his curve. He picked an NGS 310 plus trip unit. IR is H, TR is 14. Long time pickup. Let's go back to the library. NGS. Let's go back to Eaton Cutler Hammer. Let's go to Eaton Cutler Hammer, NG. There we go. Let's look at what he said. He's got an NGS 800 trip. NGS 800 trip. End frame 800 trip. There's an NGS. He may have a different library than me too. That's the other, sometimes when we've updated the libraries, you may have a difficulty finding. Here we go. NG. 310 plus. That's what he said. So he had an Eaton breaker. Let's go back. An NG frame 310 plus, NGS, 800 amp, 800 amp. Let's try this one. See what that says. And his IRH was 800 amps. IRH, right? IR was H. TR was 14. Put that on 14. TR is 14. LSD, short delay, 9. Short delay, ISD is 9. That's moving this curve here. Okay. We're getting there. Instantaneous, LI is 6. Fixed. All right, so let's do this. I'm going to delete this label. I'm going to delete each of these labels. Delete. And delete. And then what I'm going to do is I'm going to run, and I'm going to do data block format. I have my TCC settings. Well, I have a TD. Where's my TD? Ooh. I don't have them. I have it on my other computer, must be. Oh, no, there it is. Yeah, close. All right, so there's that. There's my TCF. I like to put the, I like to go up. I like to put my upstream device first and then down. So I have an NG 310 plus, IRH, TSD, fixed, LI. 4800. So let's change that device. Probably picked an LSI 800. LSI is long time, short time, instantaneous. I believe the TR was at 12, and I believe his ISD was at 7, and his instantaneous, let's go back to his instantaneous, and then LI. I still have fixed. But in any case, let's see what it looks like. His LI is fixed. 4800 amps. I'm not sure exactly which breaker he took. NGS 240. So in any case, I tried to get it exactly the same. I'll try this one. No, I don't think this was it either. H. Oh, yeah, there it is. Found it. See that? And his LI was what? His LI was 6. So let's move that LI down to 6. And we had H, and I think the TR was 14. TR was 14. ISD is 9. ISD was 9. There it is, instantaneous and 6. So this is exactly what he had. And I know that if I put my mouse cursor right here on this leading edge, that number is 3,988.3. 3,988.3. 3,988.3 amps. So what we do know is that at this bus, I will selectively coordinate from 0 to 3,988.3 amps. Anything greater than 3,988 amps, 0.3, at that bus, and the FD200 will not selectively coordinate with the NG 310 plus trip unit. What could I do to fix that? I could take this and turn the instantaneous up higher, right? Look at that. I could go up as high as 12,504 amps. So I could adjust instantaneous up, I short circuit equals 0 to 12,000. Oh boy, 12,307.4. 12,307.4. So if I move my instantaneous up on that circuit breaker, I can selectively coordinate up to 12,307.4 amps. If my fault current at my three-phase bolted fault current, if it's greater than 12,307.4 amps at that bus, then I have to do something different. I have to either go to my selective coordination tables to find for the NG 1200 or NG 800 upstream of an FD 200 to see what they selectively coordinate to, and that's based on test data. Or, yeah, I know. Well, I'm not calculating fault current, Ryan. I'm just looking at a trip curve and being as accurate as I can. My fault current, if it was 12,307 amps, I would say you selectively coordinate. If it was 12,308, then you do not, because that's greater than 0.4. So in any case, that's how I would approach this. So my answer to this person's question of, hey, Tom, is this an example of, can I say that these do not selectively coordinate? My response is, what's the fault current? Now, the chances of that GHB downstream of an FD200, the chances of you being greater than 1,832 amps, I would say that's a good yes, you may not selectively coordinate. Now, how would I make that one coordinate? I could replace that GHB fuse or replace the GHB device with a TCF fuse. Same amp rating. I don't have to change anything else in my system, and I will selectively coordinate up to the interrupting rating of this FD200. And if I wanted to know what that is, I think it's 65,000. FD200 interrupting rating. Series C FD. Let's take a look, and I should have the interrupting ratings here, I would think, on the TCC curves. Maybe, maybe not. Let's take a look. I might have to actually go to the catalog pages, but in any, here we go, FD200. There's the 30, and we have a separate trip curve for each of these devices. So this is what I'm looking at. So I'm going down through, so you'll notice this is an 80 amp FD circuit breaker. Okay, so I'm going to go to the 200, 100, 110, 150, 150, and this is, what is this one? It's a 15. FD 20, 25, geez, oh man. 25, FD 200, FD 45, 70, 90, 150, 175, 200. Here she is. Wow. And what does it say? At interrupting rating for an FD at 240 volts, which we were at 208, right? I think we're at 208, 65,000 amps. So I have an interrupting rating of 65,000 amps. That means that when I put this fuse downstream of that FD200, I'm good up to 65,000 amps at. So if I did this, Control CV, and I took that device out and put in a fuse, let's draw a fuse. This is how we do a fuse. Watch how we do this. We got to make it yellow, right? Control CV. We do two of these puppies, put one over top of the other, and then we do Control CV and bring that down here. Control Shift, Control CV, and bring that down here. Bring that to the front. And now we have a fuse. So, and that would be a TCF 30. So if I did this, then I put a TCF 30 downstream of an FD to 65 KA. I selectively coordinate up to 65,000 amps. I know that the TCF 30 fuse will go before the FD 200. And if I put a TCF 200 fuse, I know that this will all work. If I change this to a 200 amp fuse, I maintain a 2-to-1 ratio, better than a 2-to-1 ratio. And then I know that NG, I won't have to change anything. So there's different ways. My message here is there are different ways to skin that cat. Close. It's called a selective fault. Pick your fault. Pick your fault. That's right. Pick your fault. And then if you get it right, you get any of these toys, anywhere between here and here, but you can't go above there. And then you might be able to get something down here too. And then I'll guess your weight. All right, so that's basically the answer to that question. So let's take a look at some other stuff. JW made a comment that says 3-phase panels in a single-phase application. So we had this question we talked about last week too. NEC doesn't apply to boats, including larger ones, but people use at least some regular commercial electrical products in boats. It could be right. So I'm not sure if he's relating to a 3-phase panel or not, but anyway. I saw an installation where to be able to switch between single-phase shore power and 3-phase generator power, you get a 3-phase panel board with feed-through lugs. At center phase, they split the bus in half in the middle of the panel board. All right, so hold on. Let me just say this. If JW is saying that there's a manufacturer who makes a product like this, then okay. But you do not want to modify a panel board. And I'm sure he's not modifying a panel board, but I just want to use that as a springboard to say, look, you don't want to take a 3-phase panel, and if you start trying to split things yourself, like cut a bus in half and then use the bottom for something other than the top, that is what we call in the electrical industry ungood. They ran the supply at the panel to a 4-pole drum switch. The drum switch made it such that, I'm going to move this over here. The drum switch made it such that on a 3-phase generator power, the center phase is fed by phase B of the generator. All right, there's no question there. It's an application he's describing, and I'm not aware of the application. I don't know that I have enough details to even speak to it. So I'm going to move that up. Irvin, thank you. Says, thank you. Really likes the classes. Greetings from Panama. Awesome. Thanks for joining from Panama. If you're out there watching this later, Irvin, thanks for the note. Juan, quite useful. Speaking to my 15-minute tech talk on selective coordination tables, which is somewhat what we talked about here. So, and I'll put a link to that down below. The selective coordination tables is what you would use to try to answer a question when you have fault currents that go above the instantaneous region. Someone did that. It was wired in Brazil. Excellent. Okay, JW was saying that he's showing how they did that somewhere in Brazil. So that's I tell you what, when you opened that panel, you were probably like, what the heck? Is use of a current limiting breaker or fuse upstream of a circuit breaker with a lower interrupting than the infinite bus of the transformer considered a series rating application requiring either tested pairs or PE? Oh, okay. Good question. Good question, JW. So what he's speaking to is current limitations. So for example, let me do this. Control CV. Control CV. Let's do this. I'm going to try to take this diagram that I already was using. Control CV. You know what we do on Fridays? Since it's Friday, it is relaxing. We can make PowerPoints on the fly because That is what we do on the technical social distancing network. It's probably not the worst thing that's been done in Brazil. I would say, JW, that I wouldn't limit that comment to just Brazil, because I've seen some stuff in a lot of different locations. We can get, I call it the MacGyver syndrome. If you know who MacGyver is, a little bit of duct tape goes a long way. Okay, so this is sort of what I think your other question is talking about. Use of a current limiting breaker or fuse upstream of a circuit breaker with a lower interrupting rating than the infinite bus of the transformer considered a series rating application requiring either tested pairs or a PE design per the NEC. And anytime, like for example, if I have this, and let's say that this is a 10 kA interrupting rating, and let's say this is a 65 kA interrupting rating, and let's say that I have available fault current right here, I don't know, 35 I short circuit. And what hey Felix, TSDN in the house. So what JW is saying, look, and I'm not showing the transformer, but he's saying, look, if I have an infinite bus, I consider infinite bus, I put a transformer up here, and I'm just going to draw a transformer, a real ugly transformer. This is how we roll when we draw transformers on the fly. Okay, so what JW is saying, let's say that I have a transformer here and I do an infinite bus calculation and I come up with 35,000 amps on the secondary. I have a 65K interrupting rating main circuit breaker. I have a 10K interrupting rating branch or feeder circuit breaker. Is that series ratings? And yes, it is. It's series ratings. Now, when you say and then you specifically called out current limiting breaker or fuse upstream, and I caution in that regard, because when you say current limiting breaker, that is a specific breaker marked in a specific manner. I don't necessarily need to have a breaker that is listed to be as current limiting. That carries some weight with it, because here's the reason I say that, JW, is because when you say a current limiting device, you're saying it has to have special labeling, it has to have the let through curves, all that good stuff. I could have a circuit breaker that is indeed current limiting that I don't list as current limiting, but yet it is in my tables as the upstream circuit breaker, because I per UL 49, I've tested it. So I wouldn't want to put myself into a position where I say it has to be a current limiting circuit breaker, because I don't think that would be accurate. If I put a fuse upstream, it's probably going to be current limiting, just because most fuses, not all, a very large number of fuses are labeled and listed as current limiting just by their nature. But there are circuit breakers, that are not necessarily current limiting, labeled, but are current limiting. Hopefully that answers that question. But yeah, that would be an example of a series rated system where the downstream device can't interrupt 35,000 amps, yet I have tested this, whatever specific breaker it is upstream, with that specific breaker downstream, and I've published that. And I say that is a 65 Ka interrupting rating. That would permit me to label that panel board as a 65 Ka short circuit current rated piece of equipment. Because remember, when it comes to panel boards and switchboards, the short circuit current rating is based upon the lowest interrupting rating of the overcurrent devices inside. And then if I do a series rated, then I can say that 10K is a 65K solution because it's being protected by the upstream device and they're working together. I would have to label the equipment appropriately. I would have to make sure that I follow the National Electrical Code and make all of that work. So you say if the 65K breaker was either a current limiting fuse or listed limiting breaker, is that still a series rated application? You can't simply say, no, okay, I get where you're going now. Okay, I'm not buying what you're selling, but I understand what you're selling. So just because the device is current limiting does not mean that you have a series rated application. So be very careful there. Remember, and I wish I had the list. Oh, well, you know what? Here, I'm going to do this. Eaton series rating chart. Series ratings. Series ratings. Okay, so what I did was I just went out there to the website. Oh, this is good dialogue. Really good dialogue. So now I go to Series Rating Information Manual, panel boards and switchboards. Click on that and look at this. Isn't it beautiful? It just brings a tear to my eye. Oh, so beautiful. Now, you'll notice that it says main breaker is 100 amps, and these are my main breakers. I have an EHD, a QBHW, a GHB, FB, and these are my downstream breakers. So, and this is the interrupting rating that I'm getting. So these downstream breakers, that BAB is a 10K interrupting rating. This GHB is 65K. And I'm telling you that if that is the upstream device and any of these are the downstream device, you're golden. Okay. Now, you can't just say, if I have another current limiting circuit breaker, or if another current limiting fuse, and it is not in this table, JW, if it is not in this table, meaning I tested them, then you cannot just say any current limiting fuse or any current limiting circuit breaker upstream of another breaker or fuse provides that series ratings. Does the current limiting properties mean you don't have to follow series? No, and that's where you're going. You're exactly. No, that does not mean you don't have to follow the series rating rules. You still, and these tables are based upon our tested data. So if it's not in this table, yet it is a current limiting breaker upstream of another breaker, or a current limiting fuse upstream, if it's not in this table, you can't use that pair to answer your question. So you have to follow what's in these publications, because we have tested these specifically. That's why we have the catalog numbers up to that current, and we maintain these. Just because it's an upstream current limiting device protecting another device does not mean it works. It has to be in these tables. Hopefully that answers your question. But that is a really good question, because you never thought about that. You know, we talk about and that would be like the up, over, and down method, right? You can't just engineer when it's a downstream overcurrent protected device like a circuit breaker. Anything that's dynamically starting to open on those currents, you can't use the up, over, and down method. Just placing a current limiting device upstream doesn't get you there. Great question. Great question. All right. And I have, so the Excel spreadsheet file. So I will also say, if you have not dropped out to my website, thomasdomitrovich.com, go out to www.thomasdomitrovich.com and sign up. And I have some reference materials out there that you might be able to leverage and use in your education process to become better engineers and electricians and contractors. Chris Folan, will the main and the branch breaker trip at the same time? So yes, in a series rated system, and again, it depends upon the amount of fault current. So if, for example, and this goes back to selective coordination, right? So let's go back to, and this is a good one because here's the thing. And what I just had up on the screen was a GHB. That's a GHB upstream. Where's the FD? FD, it's simple and free. An FD breaker upstream of a BAB. So let's do this. Here's what I'm going to do. I'm going to plot an FD. This is this FD 200, and I'm going to kill this one. You know how you say it? You say destroy. You use destroy. I will destroy this one. It is gone. I have destroyed it. I am going to destroy this one. It is gone. I am going to destroy this one. And it is gone. Okay, so now I have an FD 200, and I'm going to put a BAB. Put a BAB, a B, A, B. I know what's going to happen, though. Thermomagnetic. And we'll say 208. And we're going to go library. Going to go to the library, and we're going to type in BAB. And we'll do a BAB 3 pole. She blows, Cupcake Island. We're going to get rid of that. And let's make it we had a 30 amp in there, so let's make it another BAB 30. Okay, so there's my BAB, and there's my FD. And now, what do we know? Selective coordination. So this is the discussion. I have an FD breaker upstream of a BAB. So an FD upstream of a BAB, they will series rate to 65,000 amps. Where is 65,000 amps on here? So if this is 1,000, that's 10,000, right? 20,000, 30,000, 40,000, 50,000, 60,000, 65,000 is way over here. And I believe I can put a flag. I believe I can put a flag. How do I put a flag? I can't remember. It's been so long. It's been so long. How do I do a flag? Anybody out there remember? Device notes, TCC settings. I know I can add a flag. Edit. Nope. Document. Nope. Run component. Where's my flag? There's my text point. Redraw. New measurement. I don't want to do measurements. I don't want to select that. TCC settings. I want to add a flag, and I don't know how to. I can't remember how to do it. Anyway. I apologize for that. But anyhow, so 65,000 amps is way up here. Okay, now hold on, boy, will the main and branch breaker trip at the same time? So here's the thing, Chris, if the fault current is less than around, what is that, 1,800 amps? If that fault current is less than about 1,800 amps, then no. It won't. So they will selectively coordinate, but you wouldn't be buying a series rated system if your fault current was less than 1,800 amps, because that BAB would be able to interrupt it, and it would be a fully rated system. The only time you're buying this series rated solution is when your fault current, your calculated bolted fault current, is greater than 10,000, right? And where's 10,000? Right here is 10,000. Okay, so right over here is 10,000. And if you're at 10,000 amps, which is the interrupting rating of the BAB, if you're exceeding that, then you know your bolted fault current is up here. If you have a bolted fault current greater than 10,000 up to 65,000, yes, they will definitely, without a doubt, both open. And that will protect and cause the, and that is the opposite of selective coordination, right? So which is why they'll tell you if you have a series rated system, it is not going to be a selectively coordinated system. Cannot be, because of the principles and fundamentals of physics and the rules. Combine those two together. Same mistake happens with SCCR ratings done by the naive. Same question, but with a non-fused disconnect. Can an upstream current limiting circuit breaker give the short circuit current protection for that disconnecting means? Wow, Ryan Jackson. Where did that come from? Great question. Non-fused disconnect. I can do an up over down protection for that non-fused disconnect because the disconnect is not a dynamic device. So if I know that, say, for example, the short circuit current rating of that equipment is 10,000 amps, that's an RMS value, and I put a current limiting fuse in front of it, then I could use an up, over, and down to provide that protection. But you may not even have to do that, Ryan, because if you look at Eaton heavy-duty safety switch, okay, let's take a look at our safety switches. When you look at the user information for a safety switch, they'll tell you it's 10K, or when protected by a specific fuse, you have 100 or 200,000 amp, or specific breakers. So now, if you have a current limiting breaker, you can use the up, over, and down and say you can protect that. But again, current limiting circuit breakers are not as prevalent as current limiting fuses. But you could engineer a solution there because it's not a dynamic device, in my humble opinion. So hopefully that helps. But if you look at the disconnect switch, and I was going to grab the catalog and whatnot and just pick and pick one of those disconnects, they'll have a short circuit current rating, and they'll tell you if it's a class whatever fuse, and whether the fuse is, if it's not in it, if it's upstream, then they'll tell you. Anyway, hopefully that helps. All right, where are we at? Man, we got some good questions. I raised a question last Friday, Tech Talk, about motor protection. Yes, I will. Motor protection. I think you were asking for a session on motor protection, if I'm not mistaken. And yes, I am going to do that. I just clicked the wrong one. Hold on. Hi, Thomas. Is it possible to have Tech Talk on protection of motors, pumps, covering the following, please? Starting current, star and delta, starting power factor, locked rotor. I will do that. I will definitely do that. So it's just not going to be right now, but I will put a program on that for you. Yes, we will handle it. Okay. I asked about both breakers and fuses that are limited. 240.86. Look at this. JW's got his book open. 240.86. That is your series rating. So I'm just going to open it up because I don't know what he's going to be asking, but we're going to open it up. There's your series ratings. All right. Only 240.86 only discusses breakers. Doesn't say if you have to have tested pairs for upstream fuses. Ooh, doggy. Tested combinations. The combination of line side overcurrent device and load side circuit breakers is tested and marked on an end. JW. So here we go. Read what it says. Okay, good. Another good question. So 240.86b says tested combinations. The combination of line side overcurrent device. Why do they say line side overcurrent device? Why don't they say line side fuse or line side circuit breaker? They chose a generic term there, but not for the downstream device. It says the combination of line side overcurrent device and load side circuit breaker. That doesn't mean line side circuit breaker and load side circuit breaker. That means line side overcurrent protected device, which could be a fuse or a circuit breaker, but you will never have a fuse downstream in a series rated pair. It will the lower rating will never be a fuse. Even if it's a class H 10K interrupting fuse, you will never have another fuse protecting a fuse. You will never have a breaker protecting a fuse. It is always going to be either a fuse or circuit breaker upstream and only a circuit breaker downstream when you're dealing with 240.86 series ratings for circuit breakers and fuses. All right. So that's why it says that. And it uses the generic term for the upstream, but it specifically says breakers on the downstream. So be mindful of that. And that's a great question. Oh, your question was based on you accidentally buying a non-eaten product. Brian Jackson, listen. All right, this is we're going to have a closed session. And please enter the confessional. Thank you for confessing that. This is what I need you to do. I need you to say 10 Hail Marys to our fathers and do something nice for about 10 people. And then you're going to need to put in 4 orders for switchgear, panel boards. Switchgear, panel boards, we're going to need a transfer switch in there, and then maybe something else. So hopefully you can make amends and do that. And remember, what you'll have to do is also wear an Eaton shirt for a week. So, and then you'll be forgiven, brother. All right? The crux is you can consider the impedance of conductor as reducing available fault current. So if a fuse is upstream, does it limit available fault current? JW. Okay. When you talk about limiting, only applies if 24086 first sentence is applicable in the first place. Where a circuit breaker is used on a circuit having an available fault current higher than the marked interrupting rating. It's exactly right, JW. I'm going to answer this one first because it speaks to the other one. It is only a circuit breaker that you will be trying to increase the interrupting ratings. That's the downstream device. So if you have a fuse, a 10K fuse, this will not apply. You can't series rate another upstream overcurrent device to address the interrupting rating of a downstream device. It can only be a circuit breaker downstream, period. So if I have a 10K circuit breaker, I can get it up to a 65K. How? I can put a fuse or a circuit breaker upstream. Doesn't matter. As long as I am doing the tested combinations, which is that booklet that I showed you. But 24086 does only apply to a downstream circuit breaker. It does not apply to a downstream fuse. So yes, it only applies, and that is correct. But I can use a fuse upstream to protect that circuit breaker. And that's in 24086B because it says a line side fuse or circuit breaker, overcurrent protective device, and a downstream circuit breaker. The downstream circuit breaker is the one that is deficient, not the upstream. Hopefully that helps. The crux is you can consider the impedance of conductor as, I think I am supposed to be on a call. What time is it? 1:04. Hold on. Yes, I'm supposed to be on a phone call. Okay. I'm going to have to pick this up. I have another meeting to be on at 1 o'clock. I am 4 minutes late, and that gentleman is probably going to be upset. So thank you for joining me for an hour. A great dialogue, great discussion. And I will be, I'm going to be teaching a class next week again. I come back Wednesday, so I might be able to do a Tech Thursday. I'm not sure of the topic yet, but I'll probably be able to go live at 5 on Thursday, and we will definitely do another Q&A Friday next week. Thank you, Chris Folan, JW, and all of you guys for tuning in. Stay tuned. See you next week. And remember, Tuesday, 12 o'clock, I believe we're going to be talking safe hazard awareness with the IAEI. So remember, hashtag IAEI News Live. Check that out. We will be, it's going to be recorded because I'm going to be presenting next Tuesday around that time. So I'm going to be on stage, but it will be broadcasted live. It will be broadcasted as a premiere video on their YouTube. And I will be talking about recognizing the hazards, 70E. You're going to want to be there at that one. Remember, and subscribe to the IAEI YouTube channel. I need to get those subscriptions up. Hurry, help me. And don't forget, thumbs up. And if you want to give me the thumbs down, you have to click it twice. Just saying. Thanks and stay safe. And remember, please stay healthy. I got to jump off. Take care. Thank you. God bless. And stay safe and healthy. And until next week. See ya.